Welcome to the new lecture. In this lecture, I will derive the expression for outage probability for a dual hope relaying system. I refer to go through my previous lectures, lecture number 8, 9, and 10, in which I have modeled wireless channel and I have depicted how random variable concept can be used for derivation of outage probability and how an amplified forward relaying system SNR derivation is done. This all I have already done in this channel, so you can refer to these lectures. In a wireless signal flow, basically, we have a user sends or receive data on wireless medium. So if there is a transmitter and there is a receiver, they connect on a wireless medium, which is undergoing the effect of noise, AWGN, identified Gaussian noise. And if X is transmitted to the receiver, it goes through fading channel H and receives received at y. So y is basically x into h plus n, where h is a random variable because it is a fading coefficient, and n is also random in nature, which is modeled for AWGN. We can also calculate the signal to noise ratio for this. Signal to noise ratio is basically signal power upon noise power. This equation has everything in power, so I will square this. So I will take expected value of mod x square, mod h square. This is my signal power basically because signal is undergoing fading, and then there is noise power. So in noise power, we basically have sigma n square, which is a statistical way of defining how much noise variance is existing in the system. And my SNR is basically signal power upon noise power. So this is expected value of mod x square, mod h square upon sigma n square, right? So this is my SNR. For a dual hope relaying system that I am considering, a source node communicates with the relay node and the relay node communicates to the destination node. So there is no direct link between the source and the destination node. I am taking a symmetric relaying to demonstrate it, which means the relay fading is used for SR link and relay fading used from relay to destination link. So both the fading coefficients are going to be uh, not identically distributed, but basically the distribution from which the random variables are taken are same. We have already derived that for fixed gain AF relaying systems, the end-to-end SNR is given by gamma 1, gamma 2 upon gamma 2 plus C, where gamma 2 1 is the random variable for source to relay SR link, and gamma 2 is the random variable for relay to destination RD link. How do we use probability density functions? It's basically a plot of density of probability. So if a random variable is denoted by capital X and the value that the random variable takes is given by small x, this graph is basically demonstrating probabilities. So if I want the probability of capital X lying between small a to capital or to small b, what I can do, I can basically find a value of a, find a value of b, and I will measure the PDF at these 2 points, fx of a, fx of b, and basically what I will do, I will find the area under this. So this area will give me the probability of random variable capital X taking value between a to b. How can I do that? I can simply calculate the integration, the area under the curve from a to b fx dx. This will be the probability of random variable x from a to b. If I take the complete integration, it will be 1 because it completes the whole sample space. All the possible outcomes are there. Another related thing is cumulative density distribution function. So distribution function is basically the probability of capital X smaller than X, which is denoted by capital F of X. X suffix X is basically the random variable and small x is the value that it takes. It's an increasing function. So again, if I want to calculate for two values A and B, I will measure the CDFs at these two values, and this time basically we will since it's this basically gives me the probability that X is smaller than A, and this basically gives me the probability of X is smaller than B. So the difference between the two will be the probability of X lying between A to B. So in this manner, I can calculate the CDF. Now the question is how PDF and CDF are related. So basically in PDF we calculate the integral to evaluate the area under the curve, while we calculate the difference between the 2 points in case of CDF. So basically CDF happens to be the integration of PDF, and the inverse function rather is that a small f becomes differentiation of capital F. Now in the present scenario, we need to calculate the outage probability of the system, which is defined as the instantaneous SNR random variable gamma, the probability that this SNR random variable falls below a predefined SNR threshold value. This is a constant value. This is a random variable. And if we want to calculate, suppose this is my gamma, signal power upon noise power, then we actually want this probability, the probability of the signal to noise ratio falling below a predefined threshold signal to noise ratio. So how can I do that? This you can understand that it is actually the CDF evaluated at this point. If we calculate the CDF at gamma TH, or rather what we do is that if we have the PDF, we integrate from minus infinity to gamma TH the PDF itself, because the integration in PDF will yield the probability, or in case of CDF, we can actually evaluate the CDF of gamma TH. But what is the random variable for which we need the CDF and PDF? That is gamma. So whatever is the instantaneous signal to noise ratio, we want its PDF and CDF. In case of our dual hope relaying system, I'm going to demonstrate this for relay random variables. So I am considering a symmetric relaying in which source to relay follows relay distribution, and relay to destination also follows relay distribution. The probability density function for relay distribution is given by for signal to noise ratio. So if gamma 1 is the random variable for source to relay link, as a function of x, the PDF small f of x is 1 upon bar gamma 1 e raised to the power minus x upon bar gamma 1, where this bar gamma 1 happens to be the average signal to noise ratio. Similarly, for gamma 2, the same expression replaced by bar gamma 2. So these are the two PDF. In the derivation, I will require CDFs also. So the CDF of relay random variable can be computed by integrating the PDF. We actually consider this for only positive values of x. So integration starts from 0 to x of the PDF f gamma 1 by d by. If I put this and solve this, this becomes 1 minus e raised to the power minus x upon bar gamma. So this expression is the CDF of random variable gamma 1 capital F. Similarly, I can also write that the CDF for gamma 2 as a function of x happens to be 1 minus e raised to the power minus x upon bar gamma 2, where gamma 2 bar is the average signal to noise ratio on the relay to destination link. Now, for the considered case, we have already defined this is the outage probability, but this time the gamma happens to be gamma 1, gamma 2 divided by gamma 2 plus c, which happens to consist of two different random variables, gamma 1 and gamma 2. So if I now uh, put gamma 1 in place, this expression, if I put it here, this is what I want. So I will try to condition this on gamma 1. So I will take everything to the right hand side. So I can firstly cross multiply gamma 2 to this side, and then I can take gamma 2 in the denominator. So it becomes gamma probability of gamma 1 smaller than gamma th 1 plus c upon gamma 2. Here two random variables are gamma 1 and gamma 2. So you can understand in this case the probability does not depend only on one random variable and depends on two random variables. And therefore we would like to calculate this using the uh, total probability theorem. The Bayes criteria is that we will calculate first of all the complete probability of gamma 1 having smaller than this value. This is basically the CDF of gamma 1, and then we will average it out on the PDF of gamma 2. So if I want this probability density function, this outage probability expression, this can be yielded by calculating the CDF capital F of gamma 1 at this complete value gamma th1 plus c upon gamma 2. But now what I am trying to justify is that I am taking a variable of integration to be y. So this gamma 2 is replaced by y, and I use the PDF of gamma 2 as a function of y and integrate for all values. This is uh, total probability theorem. I am firstly calculating the marginal case for CDF of gamma 1 evaluated at this point and the PDF of gamma 2. So this is the way it can be evaluated. Now we want to substitute both the values. We need the CDF of gamma 1 and PDF of gamma 2, which I have already introduced in previous slides. So this is my integral for outage probability. So I will replace first of all capital F of gamma 1, and whatever is x here is replaced by this term. So it becomes 1 minus e raised to the power, in place of x I write gamma th 1 minus 1 plus c upon y, and 1 upon bar gamma 1 comes from this place. and this is f comma 2. So this basically needs to be multiplied by these 1 and e raised to the power. So that I will do. So it is multiplied by 1. So this is complete integration of PDF, and this is integration of exponential function multiplied by PDF. Remember, the PDF we are evaluating for gamma 2, which is also exponential function. But when I am integrating gamma 2 y as a function for with respect to y for all values, it can take, this is basically integration of the complete PDF. So this is basically 1. So if I write that, it becomes 1. This can be replaced by 1. And this integration also, understand that I want to calculate with respect to y. So I can take everything which is not y outside. So if I multiply this, this term comes out, and remaining this term still remains inside. And we need now to substitute the value of PDF, the function of PDF of gamma 2. So that I can do. And I can, this term again comes out 1 upon bar gamma 2, and I can now have this integration is from 0 to infinity e raised to the power minus y upon bar gamma 2. This is coming from here, replacing x by y, and this is coming from this expression e raised to the power minus gamma thc upon bar gamma pi. Now, basically what we need is to evaluate this integral as a function of y, this complete integral, this everything comes out. Now, these kind of integrals are not attended directly, they are actually evaluated using some tables. So if you have done some prior work, you will understand that this is the tables of integrals that we generally refer to. Suppose Gradson, Rajik tables of integrals. I am referring to one equation. You can check that this equation number. So in this equation number, this identity is given. This identity says that if I integrate 0 to infinity y raised to the power v minus 1 e raised to the power minus gamma y e raised to the power minus beta upon y dy, then I get 2 times of beta upon y raised to the power of v by 2 Bessel's function, modified Bessel function of second type of order v. This is v. Uh, and the argument becomes 2 times of the square root of beta gamma. So if I compare this integral with this integral, you can see it is y raised to the power v minus 1. There is no y. So therefore this v becomes actually 1. When I make v1, it becomes 0. V raised to the y raised to the power 0 is 1. Uh, the thing that is multiplied by e raised to the power minus y is termed as gamma. So my gamma becomes 1 upon bar gamma 2. And similarly, the thing that is multiplied by 1 upon y e raised to the power 1 upon y is beta. So my beta becomes gamma THC upon bar gamma. So you can see the color coding also that I have done accordingly. Basically, the three constants becomes gamma is equal to 1 upon bar gamma 2, beta is equal to gamma TSC upon bar gamma 1, and b becomes 1. So if I use this, I can now write the closed form expression for the outage probability of the dual hoop relay system in which both source to relay and relay to destination links are undergoing relay fading. You need some mathematical manipulations. Please do write in the comment if there is something wrong. But I think this is what you will get because this part will come here. It is 1 upon gamma 2. It will be 1 upon gamma 2 raised to the power v by 2, so zero point 0.5. So it will cancel out. You may have this 2 also will come here. So this 2 will come. Bar gamma 2 raised to the power zero point 0.5 e raised to the power minus gamma th upon bar gamma tsc upon, right? So bar gamma 1 raised to the power half and modified Bessel's function evaluated at 2 times of beta into gamma. So beta into gamma becomes gamma TSC upon bar gamma 1. This is bar gamma 2. Sorry, this is bar gamma 2. So in this manner, we can always derive the closed form expression for any dual hope relaying system. Hope this lecture has uh, helped you to gain knowledge that how analysis is performed. In previous lectures, I have already discussed how signal to noise ratio is derived, but this is one step ahead, and this is the final exact closed form expression for a symmetric dual hope relaying systems. So I do hope this lecture helps you. Please like and subscribe if it has,